You are planning to use electricity or electronic in your projects, but you find yourself surrounded by many concepts without a clear understanding? Don't worry, in this video, you'll discover the simplest way to grasp the fundamentals of electricity. You'll learn how this wheel explains all aspects of electricity and why many circuits heat up during operation. I'm Juan and welcome to Master of Juan. Let's start with a simple question. Which of these two balls has more energy? Both are still at the same height. But which one has more potential to release energy if I move one upwards? None, because both are at the same height. Okay, then potential energy is the capacity of the ball to release energy, for example by letting it fall from the same reference point. The higher it falls, the more energy it can release upon impact. And this is noticeable in the deformation of the ball. Let's imagine that in this ball we have this amount of beans, and each bean is an electron. We'll call the ball a charge Q. Now, to make this experiment more visual, let's also assume that this ball is the size of a water droplet. I have this container with 5 liters of water. For the concept, let's say I have 5 liters of charges Q flowing from one container to another over time. From the initial experiment, if the container is at a lower height, it has less potential to release energy than a higher height when opening the valve. This is voltage in electricity, measuring how much energy charges can release, and its unit is volts. A common battery can provide 1.5 volts, meaning it lifts the container to a lower height than a 9 volts battery. We have our container, but how fast can I move the liters of charges down? Let's see. If I have a small hole, the water will take much longer to empty than with a larger hole. It's important to clarify that a source like a battery must be able to move the water from bottom to top for the cycle not to stop. This is current, how many charges I can fill it in a certain amount of time. The higher the current, the more charges per second, and its units is amperes. So far, voltage and current are generally capabilities that our source can deliver, but we need to consider a crucial factor, the properties of the medium through which the charges move. In our case, the hose through which water flows. If the hose were ideal, then the walls are completely smooth, and the charge moves smoothly over them. But if the walls are rough, then passing through them will cause collisions, creating disorder in the hose, and thus slowing the flow of charges. With this device I can alter the uniformity of water flow, increasing the resistance in our system. This is resistance, the opposition to the passes of charges. Every object, depending on its material and length, will have an electrical resistance measured in ohms. Here is where everything makes sense. There's a way to relate all these concepts, and it's called Ohm's law, which states that by multiplying current by resistance, you get voltage. In our system, if I maintain the high low voltage and squeeze the hose to increase resistance, it takes longer to fill, meaning the flow of current is lower. Another option could be to keep the resistance the same in the hoses and increase the high low voltage, increasing the current. This is great because it means that with two variables, we can determine the third with a simple math operation. Let's test the concept in a real electric circuit. For this, we need a source. We'll use the source from the previous episode, but you can also use a battery. For resistance, we'll use the resistor, which, according to the multimeter, is 47 ohms. This will be the diagram of our circuit. The 47 ohm resistor connected to a 3 volt source. And this is how we will look in real life. Calculating the flowing current is as simple as using Ohm's law we already learned, and we get 0.06 amps. When energizing the system, we see that the source effectively indicates this amount of amperes is flowing, thus confirming Ohm's law. What about if we change the voltage to 4 volts? Both the math and reality agree. This is the power of Ohm's law. Speaking of power, now comes the fun part. These 3 volts tell us that our charges fall from a potential energy height equivalent to 3, and the 60 milliamps indicate how fast those charges fills the lower container. So, if I multiply voltage by current, I see how much electrical energy per second I'm releasing. This is called power, and is measured in watts. Look what happens if I connect a 3 ohm resistor to the 4 volt source. The source indicates it's providing almost 6 watts, causing our small resistor to burn. This happens because this resistor can withstand a maximum of 1/4 of a watt. Knowing about power opens up many possibilities, like connecting a motor to convert electrical power into mechanical power. In this case, our source is providing a motor with 1/2 watt at 5 volts. So our motor delivers a mechanical power of 1/2 watt, right? Well, not really. Some of the power dissipates as heat. This is the law of conservation of energy. In the end, all the power that enters the system eventually comes out, although many times not in the way we want, as in the case of heat. Here I have an electronic component known as a linear regulator. In summary, if I have, for example, an 11 volt source but my circuit is designed to work at 5 volts, I can put this device in the middle to lower it from 11 to 5 volts. Now I can power my 5 volt motor with an 11 volt source. My source is delivering more than 1 watt for this task, but by measuring the current reaching the motor, I can calculate how much power it consumes, which is still the 1/2 watt from a minute ago. So, where are those almost 0.6 watts lost? This power is present as thermal power, heating up 30 degrees above room temperature. If you want to see more content about thermal power, subscribe to this channel. And also check the free Maker Mail in the description where I publish extra useful information for you. Okay, but there must be a better way to do this, right? Yes, if we use this device called DC-DC regulator, whose function is the same as converting 11 to 5 volts, we see now that our system is only missing 0.3 watts. Still, these are in the form of heat. And we see that they are barely 2 or 3 degrees above ambient temperature. If you enjoy math, you can have some fun with these variables and formulas. And you'll get all sorts of variations. There are quite a few. But if you're not in the mood, you can always turn to the Ohm's wheel. It has all the formulas you need to grasp electricity. And it looks really cool too. This experiment proves that expecting to get the same useful power output as input is not possible in the real world. In other words, achieving such efficiency is not possible. Efficiency is always less than 1 since the output power is less than the input, and it's often expressed as a percentage. Analyzing the motor experiment, we can find that the linear regulator has an efficiency of 45%, while the DC-DC has a 60% efficiency for this case. Not only in electronics, but in all branches of engineering, the goal is to achieve systems with efficiency as close as 100% as possible to make the most with the resources at the lowest cost. Now that we understand electricity, we can apply it to projects involving LED strips or design and implement our own circuits. To do this, you need to solder wires and components. Let me show you how to achieve professional grade soldering with simple, affordable tools that are within our reach. Click on this video to master the art of soldering.